Okay, well, hello everyone, and thank you for joining our webinar today. I'm Ed Robeck, Director of Education and Outreach for the American Geosciences Institute, AGI, and also the Director of AGI's Center for Geoscience and Society. At the end of April, AGI and the National Association of Geoscience Teachers, NAGT, will be hosting an education summit meeting at the NOAA headquarters in Silver Spring, Maryland, entitled Implementation of the Next Generation Science Standards at the State Level, which will focus specifically on the Earth and space science portions of the NGSS and what the geoscience education community can do to support K-12 teachers working to implement the vision of the NGSS. The summit is being funded by the National Science Foundation and the Center for Geoscience and Society. In preparation for that summit meeting and to support the geoscience education community more generally, the conveners of that summit asked Dr. Michael Wysession to provide this webinar. Please feel free during the webinar to type questions or comments into the chat box at any time. As time allows, John McDarris and I will pose those questions to Dr. Wysession. And you should know too that this session is being recorded and will be available at the Summit webpage for viewing in the future. It's now my pleasure to introduce Dr. Michael Wysession. Dr. Wysession is an associate professor of Earth and Planetary Science at Washington University in St. Louis and author of numerous science textbooks published by Pearson, Education, and Prentice Hall. He was team leader of the Earth and Space Science writing team for the Next Generation Science Standards, and today he will be sharing about the broader priorities and intentions of the Earth and Space Science portions of the NGSS, while also moving through some of the basic structural elements of those standards. With that, I'll turn it over to Dr. Michael Wysession.
All right, thank you very much, Ed. Can people hear me okay?
Yes.
I'll take that. Okay, I'll take that as a yes. It's a real honor to be speaking to people here. I just scanned through the list just now, and I see there are people who are involved with the Earth Science Literacy Principles, the NRC Framework for K-12 Science Education, and even going back to the National Science Education Standards. Hi, Bob. And so there is and looking at the list of names here, there is a tremendous amount of experience and knowledge and dedication concerning earth science outreach here. So I really feel very humbled to be speaking about this, and hopefully I can provide some insight. I am in a sort of unique position, having been through the Earth Science Literacy Principles, the writing of the NRC framework, and then the actual writing of the Earth and Space Science Standards at Achieve, to sort of see how the progression of this project has changed and altered and also grown and progressed over time. And hopefully I'll be able to provide some insights. Feel free to send in questions. I might not be able, I've done this, I taught an online course in this format, and sometimes I forget to look at the chat box and I just get wrapped up in what I'm saying. So maybe, Ed, if you want to monitor the comments and if there's something that is timely, just go ahead and interrupt me, because really I want to make sure that I answer your questions. And that's the key thing here.
I'll take care of that.
All right. Let me start off with a question. I'm going to come back to it. This is an old study that I'm sure many of you saw back in, 10 years ago almost now. What percentage of Americans said that they thought that genetics and evolution were real? And many of you know that the answer to this was, in fact, 40%. And what was more alarming was that this had come down from about 45%. And of course, the only country out of the 34 surveyed that had a lower percentage was Turkey. So we have one of the most fundamentalist populations. You also, I'm sure, were aware of the changing results from PISA. This is one that came out in 2012, and you can quibble about the numbers here for various countries and the equity and how some countries test all students and some don't. But the point is inescapable that if you look at math and science, we're right about average in terms of our 15-year-olds here. And there is a real issue here because we have still a top, arguably the top, graduate level science research program in the world. Given druthers, graduate students from other countries around the world will more often than not choose to come to America to do their research than any other place. And yet we have a public that is far below average in its appreciation and understanding of science. So these two are obviously not compatible in the long term. And it's in this framework that the Earth Science Literacy, the NRC framework, and the NGSS were done. Very important conversation was had right at the beginning of the NRC framework discussion at the National Academy. There was a Maryland physics professor, David Hammer, who gave this sort of crushing story in two parts about studies of air pressure. And one, he talked about a little elementary school girl who was given a juice box that was emptied and taped over and was asked to say why it was that the box didn't crush when you squeezed it. And she didn't know about air pressure, but she had all sorts of hypotheses, some of which were in left field, but it didn't matter. She was thinking, she was dropping it, she was tossing it, she was squeezing it, she was putting it in water. She was trying to come up with a variety of tests that could do this. And then at the end of this, a teacher comes over to her and says, yes, well, we know what this is. It's called air pressure. And she puts the juice box down and goes, oh, and walks over and does some other activity. He then contrasted that with his own class of physics majors at the University of Maryland, where he had given them a homework problem to determine the difference in air pressure at the ceiling and floor of the room they were in. And instead of trying to think about the problem, they immediately get their physics book and start flipping through the pages to look for the right equation. And one of them, this is a physics major, actually said, maybe we should use PV equals nRT. I think R is radius of the Earth. So someone who clearly had no understanding of the ideal gas law. Or the point being, somewhere between that girl in elementary school and those physics majors in college, we fail our students. We no longer have them feel that science is about asking questions and testing. We think it's about knowing facts and looking up things in a book to find the right formula. And so this was a big motivation, is to get back to this sense of inquiry in a broad sense of practices in science. Another question for you. In what year were the first science standards used for secondary education in the U.S.? 1852, 1893, 1965, 1995 to 2013. Well, it turns out it's actually 1852. This is back when Horace Mann in Massachusetts first adopted the Prussian standards from Frederick the Great, which were quite advanced. He was a big advocate for general education. So we've been using standards for a long time. Let me ask you another question. Many of you probably know the answer to this, but following what year did high school science begin to primarily consist of biology, chemistry, and physics, relegating geology to some physical geography in middle school, and essentially omitting astronomy from the entire middle school and high school curriculum? This goes back to 1893. This is Charles Eliot from Harvard and 9 other university professors on the Committee of 10 constructing this fabulous set of standards for students coming out of high school into college. There were great ideas. The standards were largely based on the physical laboratory experiments that students did rather than the things that they knew or memorized. They even suggested that all students spend one day outside investigating the natural world and nature. But again, geology didn't really have a framework like plate tectonics or modern earth science to hang on, and so geology got essentially left out, and they, were taught some physical geography in middle school. I probably shouldn't belabor these points about standards because I realize I'm speaking to the choir here. Most of you are critically aware that our standards in most of the country are content-based and have led to this sort of crushing memorization of factoids to answer multiple choice tests. Schools stopped teaching weeks before tests in order to prepare for school tests. The big concern is the curriculum now has become a mile wide and an inch deep. We have courses that are about science in high school and in middle school, and not actual science courses. And more than anything else, it's boring. And Stephen Pruitt at Achieve used to really like this analogy about baseball and softball, and he may have gotten it from someone else. But imagine that you wanted to teach kids to play baseball and softball. You put them in a classroom, you taught them the rules of the game, the dimensions of the field, the statistics of their favorite players, and after a couple of years, the students who were really good at memorizing this went into an honors class where they got to learn even more facts about the game, and you would stop, periodically and have them cram for 3 weeks before a multiple choice test, whatever. At the end of this, how many students are going to want to play baseball, let alone be able to play baseball? Why do we think this would work for science? And the key here is you learn baseball by getting out, grabbing a glove, getting out on the field, and playing baseball and softball. And many kids can rattle off statistics of the game and of their favorite players, but it's not because they learned it in a classroom. They learned the game first by doing it, and then they developed a love for it. So how do you do this? Well, one thing that was very important, of course, throughout the philosophy of the NGSS was information from science education research, things like taking science to school, Ready, Set, Science, turning classrooms into active research learning areas or research-like learning experiences for students. It was also tremendously informed by the work in the areas of learning progressions, and of course the idea with learning progressions, such as in these documents, that if you want to, let's say, go to the end here and you want students to understand that insects have unique structures, behaviors, and basic needs, they're all related, yet have lots of variations and complex life cycles. You don't start with that. You start down here. All insects have characteristics to perform certain functions. And as students can do things like match-associated functions, complete T-charts, sequence various aspects of an insect life cycle, you then begin to go through this progression. Unfortunately, almost none of this research actually exists in the area of Earth and space science. Well, some in space, very little in Earth science. Most of this tends to be in physics or in biology. So while we kept this in mind, we couldn't actually use it to directly inform either the NRC framework or the NGSS. And the only thing I can say is when the NGSS, and I can't wait for it to be revised, which will be 15 years or so. I mean, it was, 15, 20 years between the NSES and the NGSS? Well, we'll have to wait probably 10, 15, 20 years for the revision of NGSS, but when it does, hopefully there will be enough real research in Earth and space science learning progressions that we can actually do a much better job of aligning content with student ability. So the NRC framework really, of course, lays the foundation for all of this. And whenever someone asks, how do I go about implementing the NGSS, I always point them first to this document. Let me send a shout out to Don Duganhaus, who is is in the room here. The Earth and Space team consisted of me and Don and Scott Linneman and Dennis Schatz and Eric Pyle. And so we were able to fortunately draw upon, let's see, I can't see my slides next. That's all right. I'll come back to it. The various community literacy documents, and we pulled the content together, and then we're involved with the framework. And the deal with the framework was it has these three dimensions of the core ideas, the science and engineering practices of science, and these cross-cutting concepts. Now, let me ask you another question. In what year were the first U.S. national science K-12 standards adopted? And though many of you know this is a trick question, the answer is never, of course. It is, in fact, illegal to have national standards. It's actually specifically written in the 1965 Elementary and Secondary Education Act. President Johnson's war on poverty was sort of part of the deal that was cut with Congress. And, you know, we don't live in a country so much as a loose confederation of states, and no state wants to be told who they can have sex with, what they can smoke, what kind of guns they can carry, and sure as heck how to educate their kids. So this is very important because, you know, this is a very important message to retain. Not a penny of federal funding went towards the NGSS. And while this had, you know, meant there were times in Achieve when we seemed like we were running short of cash and you know, and had to go and beg the Carnegie Foundation of New York for more money. They footed the bill for most of this. It has actually kept us out of the fire of the Tea Party. So, you know, much of the flack that the Common Core has gotten recently is that there were these race to the top funds that Arne Duncan and President Obama put forward for race to the top, and the states that did well on this 500-point ranking system, they got these race to the top funds, and then there was criticism that the only state west of the Mississippi that got any funds was Hawaii, Obama's home state. There was all this sort of mess that happened as a result of these federal funds. Well, we got nothing from the federal government. This was a states-led process from the beginning to the end. You know, the NRC is sort of loosely associated with the government, but again, they're sort of just like mercenaries. I've been on a couple NRC committees, and we just look around at, you know, trying to beg people to give us money to write reports on things. So the Carnegie Foundation gave the money to write the report, and there were actually other organizations that funded the report as well. And 26 states participated. Now, I remember when Stephen Pruitt went out looking to get a few states to help write the process, because that would give it a little bit of oomph in later adoption if states actually participated. He was hoping for 5 or 6 states. Within a week, he had almost 20 states volunteering. And he cut it off at 26, where more than you could say, more than half the states in the country who were participating. And this figure, it's from Achieve. It's unfortunate that all these states are blue because, in fact, many of these states are red states. And if you, at the time that this was done, things shifted a little bit with later elections. I think there were 13 red and 13 blue states. So this is truly a bipartisan effort. And that's really important. I'll come back to the states that have adopted the NGSS at the end. But let me at this point just point out that there were all these states of different types, huge variations in demographics. There were also, however, representatives from states like Texas and Virginia, states that, you know, along with North Dakota and Hawaii said off the bat, Alaska and Hawaii, that said off the bat they would have nothing to do with the NGSS. There were representatives from these states on the writing team, so we had a huge variety of experience with different state standards from the onset. is the picture I often show, and so here's the earth science literacy principles, the community effort done, oh my goodness, 7-8 years ago. Someone reminded me how old this is. It's almost coming up on 10 years. It's actually probably time to do a revision on this, but that's a whole other discussion. And this, along with, do I have the other picture? No, I don't, sorry. The climate science principles, atmospheric science, and ocean science, these community-driven frameworks of science literacy directly fed into our work in putting the key concepts together, the big ideas of earth and space science for the framework, which directly fed into the writing of the NGSS, and now, of course, we're in all the, we've really begun the process, and that's why we're here today. I show you this page from the Earth Science Literacy Principles for one big reason, and that is to show you that we ended up, when we did this, putting in 3 levels of content. There were these big ideas, huge things. Earth is 4.6 billion years old. And then each of the 75 supporting concepts had, and the green doesn't come out so well here, but a first sentence that's in green type here, Earth's rocks and other materials provide a record of its history. And then there's a third level that goes into a lot of the detail. Earth scientists use the structure, sequence, and properties of rocks, and so on. And I want you to just remember that, because this was where we ended up choosing the structure for the NGSS that we have now, which also involves these 3 tiers, 3 levels, these 3 tiers of content and structure to the actual standards. All right. So at the NRC framework, there was the content of science, and that's what the writing teams at the NRC were involved with. And it was broken up into physical science, life science, and earth and space science. A lot of discussion about, should we even have silos? And you'll notice the physics and chemistry are gone. They're broken down. And there was a lot of talk about trying to do this without silos at all, and realize that it was just going to be too difficult. The thing that was very heartening from the beginning, one of the first meetings at the NRC, I felt like the earth sciences were at a disadvantage, because there were these Nobel Prize-winning biologists and physicists, Studley Hirschbach, a Nobel biologist at Harvard, and at that point there wasn't anyone on the actual NRC committee from earth science. Tanya Atwater ended up being involved, but she was brought in almost a year later. And though she turned out to be a fabulous advocate for climate and climate systems, and really helped push to make sure climate had a strong place in the framework. And so I was worried, because I was the only earth scientist in the room when we first started talking about the premise that these were supposed to be all standards for all students, so we were just going to teach the important stuff. And what was the important stuff? And I was ready to, like, oh my God, we're going to have mitosis and meiosis, and there's going to be nothing about earth science. When we went around the room, the things that these physicists and biologists and chemists said were most important were environment, resources, human impacts, human sustainability. So there may be pushback in the K-12 level, particularly in high school, physics and chemistry teachers who don't want to teach earth science and don't value it. But you get to the Nobel Prize level, you get to the National Academy of Science people, and the people in that room were all strongly in support of earth and space science. So the premise from the beginning was high school science would be a year of physical science, a year of life science, a year of earth and space science. And so this is a huge departure, and it was right from the bat, and the earth scientists didn't have to push for this. So the NRC framework that was written, I just flipped through, imagine I'm flipping through the book here from it, and I just want to point out that what really informed the next phase were these grade band endpoints. that were done for by the end of second grade, by the end of fifth grade, by the end of eighth grade, and by the end of 12th grade. And this was the work that largely that the Earth and Space team did with some tinkering by Tanya and Helen Quinn after the fact. And Rick Duschel got involved in at this at some point also, education expert at Penn State. You will notice if you do a point-by-point correlation, and no one has actually done this yet, and I keep meaning to do it as soon as I find some free time. Not every one of these disciplinary core ideas, as they're called, ended up in the NGSS. There was this the horrible purge, or whatever you want to call it, the slashing back of standards between the January 2013 draft and the actual release of the NGSS in April of 2013, where essentially we had to cut the number of performance expectations in between a third and a half. And some of the actual disciplinary core ideas got cut out as well. Not many. Mostly we ended up, frankly, merging a lot of the performance expectations. But you will, if you look carefully, you may find places where some of the content in here didn't actually make it into a standard, which sort of puts it into this funny limbo that we don't know what to do with, where the NRC framework had said this is essential for all students, but it's not actually in the NGSS. All right. Bob Ridke's here and could speak to this more than I can, but the NSES was published in 1996, and it's interesting. If you do a comparison of the two documents, there's very little that's in the NRC framework that wasn't in the NSES back in 1996. The ideas of the importance of science practices, human content, society-relevant things, even aspects of sort of design and the sort of mix of science and engineering. But the practices were in a different section of the book than the science content. And the human society relevant aspects were in a different chapter than the rest of the Earth and space science. So what happened is, following 1996, this is a very influential document. States looked at this, to develop their state standards. They grabbed the content, and they probably didn't bother to read the rest of the document. Well, that is sort of what we did in the framework, where there's chapter 3 that lists out all the content, and the practices are in another chapter. And then there's this little short section that's just a few pages long that says actual standards need to have the practices and the content interwoven with these broader cross-cutting concepts, these 3 dimensions that were really Helen Quinn's big, this is what she spoke about all the time, and she was chair of the NRC committee that did this. But the real difference is the NRC framework for K-12 education was followed up by the NGSS. There wasn't a parallel project that actually took the full advice from the NSES and developed a set of standards. And so the NGSS was this, coming to fruition of the ideas that were in that NRC framework. All right. The writing team for NGSS is very different than the writing team for the NRC framework. You had Mary, so here's the Earth and Space Science writing team. You had Mary Colson, who's a brilliant educator, middle school teacher from Minnesota. Ken Huff, who had won the President's Award for teaching, really into space science, also middle school teacher. Paul Speranza was retired, a high school teacher from New York State. Paula Messina is a professor at San Jose State, works a lot with professional development for middle school and high school teachers. As I mentioned, Rick Duschel at Penn State is an expert in geoscience education. So you had a real mix of skills here. You'll notice there's no one from elementary school here, and this is a serious problem with the NGSS, something that really needs to be resolved in the next revision. The elementary school group was written by a totally different team of the standards. It was interdisciplinary from the start, which is a positive thing. So there wasn't a earth science, life science, physical science for elementary school. The elementary school was done as one unit. But because we were always in such a huge rush for time, there was a tremendous inadequate communication between our group, which did the middle school and high school earth science, and the elementary school group, and also the physical science and life science groups. We all kind of worked in our silos, and then, tried to shuffle things around as best we could at various times. Sorry about this picture here. I couldn't find a picture of Paul, so this is notes, a photograph from the board on one of the days when we were trying to put all this stuff together. I think I'll actually show that picture in a moment. So that's just something to be aware of. There are some kind of rough connections between, the middle school to high school flows well because the groups in earth and life and physical did both of those. But the connection between the earth, between elementary and middle school is a little bit rough at times. Right. Okay, humorous interlude here. I'm going to sort of just show you part of what the walls look like as we tried to do this. So this is at the NGSS. We're taking the big ideas here from that you can see from the NRC framework, the three big ideas of sort of space and time, the second big idea, Earth systems, the third big idea, which is human impacts, resources, hazards, climate, human impacts on Earth systems, and then tried to sort of break them out. We first wrote them out neatly on cards, and so we had this sort of nicely categorized. And then we tried to group them together, and we sort of had some frameworks. Here's the water cycle here with oceans and weathering and erosion and atmosphere, and we got to put some physical science in there, and there's some life science in there. So we started borrowing cards from the life science, that was green, and the physical science, that was orange. And then all of a sudden, we started grouping those together. Yellow, by the way, is engineering as well. And we couldn't end up actually fitting it in 2 dimensions. So we began sticking push pins up into the ceiling and dropping strings down and connecting strings between the wall and the cards. And we would sort of walk in between this sort of 3D structure of stuff hanging down from the ceiling. Earth science is tremendously interconnected, and to try to actually, summarize the earth science into a few succinct performance expectations was a daunting task. If anyone here has been involved with, the AAAS maps, like Project 2061, you know exactly what I'm talking about. So this is what we ended up with. Elementary school, grade level, integrated across all sciences. We thought of doing grade level at middle school, and in fact, we began actually going in 2 different directions, having both grade banded, which is what we ended up with, just middle school, and grade level, 6, 7, 8, because when we began this process, the whole thing about like too many cooks in the kitchen, we had 26 states, each giving us feedback. And some of the states clearly wanted middle school grade level, and some wanted middle school grade banded, and it just got so complex with all the different versions, we gave up on this. So we thought maybe at the end we would go back to a grade level standards for middle school, maybe even for high school. We never had the time. We never got to it. So it is grade level in elementary, but 6, 8, 9, 11 for middle school and high school. I'm betting most of you have seen this page. And if not, right when I'm done, please go to the Achieve website and download these and take a look at. This is one performance expectation, this whole page. And I'll just run through the motivation behind this a little bit. So this is high school. It's the third big idea of Earth and space science. So this is ESS 3, and this is the first one, the first performance expectation in that big idea of Earth and human activity. Every one of the performance expectations begins with the root, students who demonstrate understanding can, followed by a verb. And in this case, it's construct an explanation based on evidence for how the availability of natural resources, occurrence of natural hazards, and changes in climate have influenced human activity. So that doesn't look like any other performance expectation that we have in states. There's nothing in here to memorize. There are no names of rivers, lakes, deltas, volcanoes, earthquakes. This is what students will be assessed on. And they will assess on being able to construct an explanation based on evidence. Now, there is content here, and here are the three dimensions. The content in this case has to do with natural resources, natural hazards, but it is intimately tied to a practice, and in this case, it's constructing explanations and designing solutions. And I should say for each of these practices, they are broken out, they are grade banded, so they progress in complexity. Obviously, we want kindergartners constructing explanations as well as high school kids, but they're going to do it in different ways. And within each grade band, there are also different forms of constructing explanations. So in this one, it is construct an explanation based on valid and reliable evidence obtained from a variety of sources, including students' own investigations, models, theories, simulations, peer review, and the assumption that theories and laws that describe the natural world operate today as they did in the past and will continue to do so in the future. So that's the motivating practice here, tied with the content. And then there is also inherent in here, though it's rarely spelled out. In this case, it's a cross-cutting concept of cause and effect, and I'll get to this in just a moment. In this case, it's empirical evidence is required to differentiate between cause and correlation and make claims about specific causes and effects. There is also this long paragraph here that's the clarification statement. This is that third tier of information that I talked about that we took from the Earth Science Literacy Principles. When we first did this, one of the earlier drafts, this whole thing was the performance expectation. And the states freaked out. They said, there is so much in here, this is so complex, we don't know what to do with this. And we were like, no, but these are just examples. We're not telling the students, that they need to do every one of these, but that examples of key natural resources include access to fresh water, such as rivers, lakes, and groundwater, or regions of fertile soil, such as river deltas, and high concentrations of minerals and fossil fuels. Examples of natural hazards can be from interior processes, such as volcanic eruptions and earthquakes, surface processes, tsunamis, mass wasting, soil erosion, severe weather, hurricanes, floods, droughts, and examples of the results of changes in climate that can affect populations or drive mass migrations include changes to sea level, regional patterns of temperature and precipitation, and the types of crops and livestock that can be raised. This is a lifetime of study. We're not expecting students to do all of this. What are they assessed on? They're assessed on whether or not they can construct an explanation based on evidence. How would you assess this? You wouldn't give them a multiple choice test asking about any of this stuff necessarily. You would give them evidence, give them a data, a graph, chart, and have them analyze it and construct an explanation based on it. So the assessment is aimed at the practice. It's not aimed at the content. And that, in a nutshell, is the whole point of the NGSS. it is, now we've kind of passed the buck in a little bit in that we've now sent the onus on to the developers of the assessments, which hasn't been done yet. But we've now said, okay, you've got to write assessments that are going to match these performance expectations. And I have to be honest, just like when we were at the NRC working on the framework, we really had no idea what these performance expectations would actually look like. At this point in time, I really have no idea what appropriate assessments to assess these will look like. But we'll cross that bridge when we get there. The other thing here that's important is it has connections to the Common Core math and literacy. And this is really key here because in some states, California is a good example. There are many places where No Child Left Behind for English and math is still the rule. Principals and superintendents couldn't care less about science. But if the science can provide the support that will help their students perform better in math and English, then sure, they're all for it. Why not? So there are some cases where we're only getting traction because people think that because it is aligned, these connections with the English language arts, literacy, and math from the Common Core were actually done by some of the leading figures from the Common Core. And I should say also that Achieve has been very active in creating math science tasks that also include literacy, to further strengthen those ties between the NGSS and the Common Core, at least as far as content goes. It's still a different process. We still want the Tea Party to leave us alone. This isn't a federal project, but those links are built in. All right. So we got into talking about the scientific method and how you do this, the steps of the scientific method. You ask a question, you do background research, construct it. No, right? So there is no scientific method. We know this. At least scientific method in the strict, sense that has been unfortunately jumped on by textbook companies to try to teach students that doing science is a cookbook formula. We know that that's not how science works. Science, the practice of science involves, we don't sit in our basements late at night in white lab coats by ourselves. Science is inherently collaborative and interdisciplinary and involves large groups of people, and we ask questions and we defend arguments and we obtain and communicate information and all this stuff. So these are the 8 practices of science and engineering, and I'm sure you have seen these before. I cringe a little bit when I see this list because now all of a sudden there are 8 practices of science and engineering. It's like meet the new boss, same as the old boss, and it's like, no, there aren't 8 practices of science and engineering, of course. In fact, we had 5, we had 7, we had 10. It's like musical chairs. By the time finally we had to write something, we ended up at 8. And there's obviously overlap between constructing explanations and developing an argument, and there's meant to be overlap. But the point is that there is a wide variety of practices, and it's set up so that in every grade level, students should have experience with every one of these. Maybe not all in the same subject. Maybe 6th grade might have some combination of life and earth and space and physical, but they will have exposure to all of these practices. The thing for earth science that I find really important is the emphasis on evidence. And I think for the workshop that's going to happen at the end of April, this is really key. Planning and carrying out investigations from data, analyzing and interpreting data, using mathematics, which is, with data, constructing explanations, as you saw earlier, from evidence, from data, engaging in an argument from evidence, communicating that evidence or information. And so this is really important for earth and space science. Our field is inherently observationally driven. And so there is going to be a real need at middle school and high school for these evidence sets, these database sets for students to analyze. I'll just spend a quick word on the cross-cutting concepts. Again, there was an arbitrary number of these, and they're very different. Actually, I'm going to sort of give you my take on the difference between them. But the idea is, and then this is very clear, you don't have a unit on patterns. It's not like you stop for 3 weeks and teach students about patterns. But as the students go through their education, if the instructors are aware of these cross-cutting concepts and can sort of reinforce them, then students begin to develop a deep, intuitive understanding of the natural world by seeing how these each play in the different areas of life, physical and earth and space. So I think of them in sort of 3 ways. There's the structure and dimension ones. There's patterns and scale and proportion and quantity. And this is sort of the deconstructionist view a little bit. Well, like I said, this is more sort of just observing, categorizing, classifying information. But there are real strengths to this, because if you have, let's say, the model of an atom, and then you have the model of a cell, and you have a model of the solar system, and the model of the galaxy, you begin to see that some of the patterns are similar over vastly different scales and proportions. And yet, much of the universe operates in areas of high density with areas of less density and big spaces in between. Now, of course, the forces operating at this level of the strong nuclear forces holding the nucleus together compared to gravity holding a galaxy together, the forces are different, but sometimes the patterns and appearances are the same, and there is a strength that comes through that. Then there's the causality of components, structure and function, and cause and effect. And these are this sort of reductionist view to taking the system and breaking it down into its individual components. And there's a benefit to that. You want to understand how a radio works. One way is to take the radio. This is an old analog radio with all the little flip numbers here. Take it all apart. Hear all the parts of a radio. You know, the transducers and the antennas and the rheostats and the whole thing. The problem is, are you going to hear any music? No. You don't actually get to see what this thing does when you take apart all the pieces. It's only by putting it together into a single system that you really see how that works. And so that's this third set of this holistic approach of systems and system models, energy and matter, stability and change, how a system operates, the tipping points, flow of energy, the cycling of matter. And the thing that's really important is then students look at sort of simplistic models of things, in this case a parallel circuit with a battery driving electrons through a set of light bulbs. And then they go and they look at a simplified model of the human circulatory system with a pump that's driving, like a battery, driving the flow of blood cells through a set of parallel circuits. And then maybe they look at a climate system where you have a battery that is driving a set of flow of matter, cycling of matter between different components. And they begin to get this sort of this progression, a deepening of understanding of how these systems actually operate. All right. And then there was a fourth area, and I have to say we had no idea what to do with this. And in every different of the different versions, and there were only 2 public drafts of the NGSS that came out. One that was in May of 2012, and then in January of 2013. I think there were at least a dozen internal versions. We'd send something off to some states, to college and career readiness. Version control just got totally out of control with this. But the engineering, the science, technology, and engineering are an integral part of the NGSS, and that's a really other important bullet. If there's one word that rules science education right now, you know what it is, right? It's STEM. And you see it everywhere. I feel like I'm in a Monty Python skit, STEM, 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 wonderful STEM. It's just like, so yes, So we have to be part of STEM with this. And the engineering and technology are incorporated in a variety of ways. And I don't have to go through the reasons that STEM is important. You know that. And, I skipped the bullets on engineering here. I trimmed this down. So I'll just say, the engineering ends up in all three of the foundation boxes now. There are actually some disciplinary core ideas, some standard pages on engineering design processes. There's not supposed to be a unit in the classroom on the engineering design process, unfortunately, but it is it's there, and if anyone wants to to incorporate that in a deeper level, they can draw upon it. The engineering also appears in the cross-cutting concepts, and it also appears in the practices as well. Poor Kerry Snyder, he was in charge of the engineering sort of design team. Every draft, engineering got bounced from one place to another. He tried something else. The states hated it, or somebody didn't like it. And we just ended up with how it's incorporated now, and really nobody's thoroughly happy with it. But again, it's the first time we've ever tried to incorporate engineering in with science standards. And I'm sure it will be very different in the revision 15 years from now. All right, I talked about math and English. Couple quick points to sort of remember with this. Wonderful opportunities for things like place-based learning. So let's come back to, or I think this is a different one. This is a middle school standard here. Analyze and interpret data on natural hazards to forecast future catastrophic events and inform the development of technologies to mitigate their effects. So you can obviously see the strong role of engineering here. And frankly, the earth and space science was a place for a lot of those engineering ideas. Whether it was big-scale geoengineering or small-scale, that merger of humans interacting with their world, whether it's getting resources, whether it's trying to mitigate the effects of everything that we do, has a huge overlap between earth science and engineering. So I think there are some real opportunities for us to pair up with engineering communities, especially sort of those engineering communities dealing with environmental or energy engineering. Those connections at university have largely been untapped for a long time. I think this is an opportunity to communicate. In this example, here we have natural hazards, the long list of different hazards. The point is not for students to have to go and learn all of these. You pick one example and you learn how to analyze and interpret data. So if you're in California, it'll probably be earthquakes. If it's Oklahoma, it could be tornadoes. If you're in Chicago, it might be, severe weather and storms. If it's in Seattle, you should learn something about Mount Rainier. If it's in Florida, it's probably hurricanes. Here in St. Louis, it might be flooding. The point is, this is a wonderful mechanism for students to learn how to analyze and interpret data. And frankly, once students get excited, they'll pick up the other stuff. But this provides teachers and students this regional enthusiasm is important. Another important point as you go through this, one of the unfortunate aspects of the cutback in total standards, and to give you an example, the middle school Earth and Space Science has 15 performance expectations. The January draft had 31. We had to reduce the number by more than half. There are actually more performance expectations in Earth and Space Science in high school. There are 19. We had many performance expectations that were overlapping with the other areas, with life science and physical science, to emphasize the fact that there should not be these silos in how we learn the science education. The states hated it. They came back and they said, it looks like we have tons and tons of performance expectations. No one's going to buy this. You need to cut it down. So essentially, we cut out all the performance expectations that have overlap with physical science and life science. There was a carbon cycle performance expectations both in life science and Earth and space. The life science dealt more with, the biosphere, and ours dealt more with the geosphere, but they were clearly meant to be taught together. No, we have the carbon cycle, life science doesn't have it. And so biologists looking through say, what? There's nothing in the NGSS about the carbon cycle. It's like, well, yes, there is. It's just over in Earth and space science now. So when people begin to construct curricula around the NGSS, and again, the way I like to think of this is, the framework is the skeleton. The NGSS are the organs that flesh out the skeleton, and the curricula are going to be like clothes that you can mix and match on a body. You can dress up the NGSS any way you want. And this is a really key point, is to bundle. This is one of Stephen Pruitt's, who headed up the project at Achieve. This is his big baby. He talks about all this time, bundling the performance expectations, creating storylines that integrate across disciplines in order to make the science have it make more sense, but also be more engaging. So, good example. This is actually, I'm working with a school district here in Missouri. And Missouri will probably never, the legislature will never actually support, vote for the NGSS, but many of the school districts in Missouri don't care. They're going ahead with NGSS anyway. Here's a bundling that we're doing on evolution. So you want to do fossils and evolution. Well, obviously there are performance expectations in life science, things that have to do with evolution, with natural selection, the emergence of new species, the extinction of old species. However, you want to find out the extinction of old species, well, you got to go to earth science. And to do that, first of all, you need to know about geologic time. You need to know about stratigraphy, rock strata. And you need to have a sense of the dating of objects starting from an ancient Earth and moving the clock forward. But how do you determine the ages? Well, you need radioactivity. So you have to incorporate in physical science here as well, in order to actually sort of match up the date. So here is a storyline of evolution, from the fossil record, where you need to combine life science, earth and space science, and physical science. And this is going to be a theme that we run throughout. All right, quick last point here I want to make. Appendix K is one of the most important documents of the NGSS. It lists out 3 or more, actually, sort of structured ways that you could combine the middle school and high school content. The ideal way, and they don't say it's the ideal way, but they present it first as course map 1, the conceptual understanding model. It's sort of like the idea of physics first. Physics first says you should teach physics first in high school because you need the physics for the chemistry, and then you follow with chemistry, but then you do biology last because you need the physics and the chemistry for the biology. Well, you need the physics and the chemistry and the biology to do the earth science in many cases, because if you want to talk about something like earth systems or climate systems, right, you need to do climate. You need to know radiation physics, atmospheric chemistry, biosphere feedbacks, space science, Milankovitch cycles, solar physics, before you can, even before humans begin to come into the scene, and that makes everything else even more complicated. So their recommendation was 3 years of science, both for middle school and for high school, largely physical science, that's the PS, in your first year. Your second, so that would be 6th grade and also 9th grade. Your second course would be largely life science. And that's 7th grade and 10th grade. I'm sorry, that came out jumbled. I couldn't hear that. No, okay. And then your third course would be largely earth and space science. So that is, whether or not schools or states adopt that, I don't know. That's put forward. I'll skip this. The second map is the easiest way that you would actually unwrap the NGSS. You would have, for both middle school and for high school, a year of physical science, a year of life science, and a year of earth and space science. The problems here, particularly in middle school, where where you put these in terms of 6, 7, 8 means you're going to be doing both simple complex concepts and complicated concepts sort of out of order. And the third map, which is for Earth and Space, just for high school, is probably the easiest in terms of workforce because you already have the biology and chemistry and physics teachers. And that is you take, here's the E, you take the geobiology and probably the climate, you put in your biology class. You take the geochemistry, you put it in the chemistry class. You take the geophysics, you put it in the physics class. And all the other geology, I don't know where you would put it, but you'd find a place in this set of courses. Least efficient in terms of instruction time. Things are out of order. You'd have to go back and reteach things. You'd have to teach concepts before they were ready. But it might be what the majority of states end up going to initially. Again, this is a process. Even if you got, frankly, if you got a year of Earth and Space Science into everybody's class, who in high school somewhere, that would be a huge advance. I always angle for having a separate Earth and Space Science class for high school. Frankly, this, what will probably happen is course map 1 will be the dominant for middle school. Things are pretty integrated already. Most middle schools have some level of integration across life, physical, and Earth and space. The course map 2 is what I'm hoping happens at high school. There are a lot of schools that have 2 years of science, not as many as there used to be, and they would be a year of physical science and a year of life science. So we could just add a year of Earth and space science. That seems pretty easy. My sense is this is what will happen for most of the high schools. But it's a process. I think this is my last slide. Right? Is it last slide? No, okay, second to last slide. The change over time, and I'm sorry I've run over, if people can just hang on a moment or so. You look at 1987, 40 states required 1 or 2 years of science in high school. There have always been about a half a dozen states that don't have any state law on this. They leave it up to individual districts. 3 states required 3 years of science. You look at 2011, that number for 1 to 2 years is down to 15. The number at 3 or 4 is over 30. Actually, there are a few more since that have switched to 4 years. Now, it's interesting. There's some interesting. Illinois has adopted the NGSS, but it still only requires 2 years of high school science. So I'm not sure how they're going to do this because there's no way you could do the NGSS in 2 years of high school. But there is some discussion of adopting a 3rd year, and maybe the NGSS will be the motivation for Illinois to switch to having 3 years. So now it's interesting, if states do 4 years, then you could have a year of life, chemistry, physics, and Earth and space. Though more likely the 4th year might be an AP, but I don't know. But that would be an interesting model to consider also. In any case, states are now at least in a position where they can actually do 3 years of science in high school. Last slide. 13 states have adopted them so far, and Washington, D.C. Other states have almost adopted them. So Oklahoma, as you may know, the governor is Republican, very conservative. Fracking is a big deal here, and they said, nope, we don't like the climate change. Everything else looks great. We're all for it. And so the Oklahoma Natural Gas Pipeline Licensing Board got to edit the climate change standards. And in Oklahoma, there is no global warming. But the other aspects of the NGSS are there almost word for word. The pedagogy, the emphasis on practices, the integration of the 3 dimensions, the emphasis on including engineering, etc. Massachusetts was a big influence in writing the NGSS, enthusiastic throughout. At the end, they didn't know what to do with the cross-cutting concepts. They cut the 3rd dimension out. Otherwise, it's almost identical. And if someone ever knows the story of why this happened, I would be fascinated to know. I really have no idea why that happened. And then there are other places. There are many school districts, states, counties, and even now other countries. I think I was supposed to do this. This is supposed to be counties. It's a typo. But other countries are now, finally, we have a sort of framework of science education that is worthy for other countries to start looking at as well. And tremendous enthusiasm. States that are not adopting the NGSS at a statewide, individual schools are moving in this direction, simply because it makes sense to incorporate the STEM with the engineering and technology and an emphasis on math, and to move towards a more practice-based approach to teaching science. And I've been working actually with the Archdiocese of Pennsylvania, the Catholic schools in eastern Pennsylvania. Pennsylvania is not going to adopt the NGSS, but they don't care. They think it's a great idea, and they're gung-ho, and they're moving ahead with it. One of the biggest areas of pushback turned out not to be evolution, but climate change. And, of course, the notable case was Wyoming, where the Wyoming State Board was really interested in the NGSS, but the governor and the state legislature said no. We're the country's largest producer of coal, and all this stuff about climate change just doesn't fly with us. They actually came out and said, we don't have an argument with the science behind it. It will be bad for our state economy, so we're not going to teach this to our kids. Which to me is crazy how you can actually get away with saying, yeah, the science of this is right, but it's but we don't like the politics or the implications, the economic implications of it. So we're just not going to teach it to our kids. But that was the case. And yet we had victories like West Virginia, which is also a very large coal-producing state, where there began to be some pushback from some sort of industry-heavy sides, and it got stemmed right away, and they said, nope, we're going to adopt the NGSS just as they are. And so West Virginia, fully adopted the NGSS, even a state that's largely coal-driven, and even with all the emphasis on climate in here. And if you look at Earth and space science at the high school level, there's probably almost half of the performance expectations deal with climate and climate systems in one way or another, and quite a few directly. All right, I'm sorry I've run over, but I wanted to get through as much of this as I could. Please, if you have questions, send me emails or give me a call. I'm happy to talk more about this, and I really look forward to the workshop. I'm really so excited to see enthusiasm from so many parts of the community coming together for this. And so I'll end there. Thank you.
Michael, thank you very much for sharing today. And there's so many dimensions to this, and you helped outline it very clearly for us. We appreciate that very much. There's so much more to talk about. Because I know some people have to depart from the meeting, I'm going to mention that shortly after we conclude, John McDarris of the Science Education Resource Center at Carleton College will send out an evaluation of this webinar, as well as some other information about how to keep in touch with the summit meeting itself and other developments in NGSS implementation, as well as a needs assessment survey that's completed online. Some of you may have already seen that, and if you have, that's fine. If you haven't, please complete that. That will help us to gauge the needs in the community. Those of you who do want to stay for a few more minutes, Michael, do you have a few minutes?
I'm just checking here. I might not be able to stay for long.
Okay. Well, then what I think I'll do is I'll.
It'd probably be best to have people sort of contact me individually, and I will answer anyone's questions.
Okay, very well. As we close, I wanted to be sure to thank the leadership of NAGT and AGI for their support of this effort, especially Kathy Manduca and Pat Leahy, the executive directors of those organizations, and the co-conveners that I'm working with on the summit, Aida Awad and Susan Burr-Sullivan, who are two past presidents of NAGT. And thanks very much to John McDarris, who's at the Science Education Resource Center, for his excellent technical support and advice on all aspects of this. And again, special thanks to you, Michael, for your sharing today and for all that you can offer us to understand this very important initiative called the NGSS. Thanks very much. We will be in touch very soon.
All right. Thank you, everyone, for participating. And again, thanks to so many of the people here who have contributed so much at all steps of everything that I've talked about. So, anyway, I look forward to continuing the work.
Okay, and I will just repeat that we will be, this has been recorded, and we will be putting this online. It will be available for replay as people would like. And thank you all very much for participating in this webinar. With that, we are done. Have a nice weekend.